Actually, I didn't mean to hit stop recording on that last one, so that's why it was such a short video. I wanted to start off this one by asking you to graph each of the following rational functions. So please go ahead and pause the video and see if you can do these fairly quickly, remembering that each of these is just a transformation of a basic function, either 1 over x or 1 over x squared, and or even 1 over x cubed, 1 over x to the fourth. So go ahead and draw these. I'm going to go ahead and show you the solutions. Okay, 1 over x minus 1 is the graph of 1 over x shifted to the right 1 unit. 1 over x minus 1 squared is the graph of 1 over x squared shifted to the right 1 unit. Now we don't really know what 1 over x cubed looks like, but this is what it looks like. It looks just like 1 over x minus 1. It's the graph of 1 over x cubed shifted to the right 1 unit. And then the same thing over here, 1 over x to the fourth looks just like 1 over x squared. A little bit steeper in the beginning there, you can see that. But hopefully that helps clarify that you guys can not have to worry about 1 over x to the third or fourth or even any higher powers. The basic shape of the graph doesn't change. Okay, and you can pause the video and look at that. Oh, I did want to make mention of some notation here. You may have noticed this down here. Each has the vertical asymptote x equals 1. And the one thing I really do want you to key in on so far here is that when, let's see, what happens to the value of r of x, okay, as x approaches 1 from the right side of the vertical asymptote. That is, we say what is the limit as x approaches 1 from the right of the function. The limit is just telling us where are the y values going, and in this case it tells us when x is approaching 1 from the right. That little plus sign right there, that means from the right. That's exactly what it says, from the right side. What happens to the value of r of x as x approaches 1 from the left side? Well, you can see what is happening with the value of the function when x is approaching 1 from both the right and the left. So looking at this guy right here, 1 over x minus 1, we can see as x is approaching 1 from the right, the values of the function are going way up to positive infinity, and as x is approaching 1 from the left, you're on the graph and the y values are approaching negative infinity. So bringing it back to the inputs and outputs, the limit is just saying as the inputs are approaching something, where are the outputs going? Okay, so we can still use the words inputs and outputs to describe concepts that you guys are learning, and we'll continue to do that throughout the course. We're going to be finding horizontal asymptotes now. We're not going to worry about the oblique asymptotes. So even in the homework or any of the classwork that we do, if you see the instructions find the oblique asymptotes, don't bother with that. Okay, and if I happen to mess up, just let me know in terms of giving you problems that have that on the test. You're not going to have that on the test, so don't worry about it. Now let's go ahead and take a look. There is a theorem. I've never used this term, but I'm going to go ahead and give it a shot this year. If a rational function is proper, the line y equals 0 is a horizontal asymptote of its graph. And all a function has to be proper is for the denominator's power degree to be higher than the numerators. Okay, so if you go back to this theorem, a rational function is proper. I should probably write that down. It'd probably be a good idea. So it's proper when the denominator, I'm going to pause it and write that. And that's all we're saying. When the degree in the denominator is greater than the degree in the numerator, then we say that the function is proper. And if the rational function is proper, then the line y equals 0 is a horizontal asymptote of its graph. Let's look at some other ones. So here's an example. Find the horizontal asymptotes, if any, of the graph. Okay, well we see that the denominator has a higher degree than the numerator, so therefore it's called proper, and therefore y equals 0 is a horizontal asymptote of the graph of this function. Okay, denominator's degree is higher than the numerator, so that's how we do that. And I guess if you took a look at the graph, you would see that the x-axis, then we don't really know how to find the shape of this graph yet. We'll get to that. But we do know that for x values really large, either the y values are approaching 0 from the bottom, or the y values are approaching 0 from the top, or they're going to keep going like this and they get closer and closer to 0, and that's still okay. It's okay to cross a horizontal asymptote, just not okay to cross a vertical asymptote. Okay, and then from the left side it might go that way, it might go that way, it might cross it and then get closer and closer. We don't know, we don't really care right now because we're only being asked to find the horizontal asymptotes. Okay? Now, here's what I really want you to write down. It's actually fairly easy to remember once you do a few of these, but it's important that you understand where this comes from. The horizontal asymptote, the ha, is what we're looking for here. And so I have a little chart. We already talked about how to find the horizontal asymptote of y equals 0. That's if we have a proper rational function in which the denominator is degree, if the denominator is greater than the degree of the numerator. Okay, and so just to clarify here what you're seeing, we've got p of x over q of x, that's our rational function. N is going to represent the degree in the numerator, the degree of the numerator. M is going to represent the degree of the denominator, okay, because each one of these is each numerator and denominator is a polynomial function, so each polynomial function has a degree, okay, so it's the leading term. Alright, so let's remind ourselves what we just talked about. If n is less than m, meaning the degree in the numerator is less than the degree in the denominator, then we have y equals 0 is our horizontal asymptote. Now, one thing you're looking at here, you might be thinking, what in the world is the word bubbles doing sitting there? Well, I like to call this the bubble theorem, and it's not named after Dr. Bubble or anything, it's just because it kind of looks like bubbles. Okay, bubble theorem. This is kind of like my own analogy of how I can remember whether we have a horizontal asymptote or not. Okay, think about this if you would, for me, humor me here. We've got the denominator being bigger, the degree being bigger than the numerator. So the size of the bubble represents the size of the degree of the polynomial relative to the other one. Okay, so in this case, having a bigger bubble on the bottom indicates the degree of the denominator is bigger than the degree of the numerator. Okay, well, when you have a big bubble on the bottom, it's kind of like it weighs down the fraction, and weighing down the fraction means that this big bubble is just going to keep it. It's like having a lot of weight. You're trying to pick up a little tiny thing is trying to pick up this big thing here, and it doesn't go anywhere, so it stays right there at 0. Okay, so y equals 0 is our horizontal asymptote. So bubble theorem when we're trying to find horizontal asymptotes. Well, let's apply that concept to see what happens when the denominator is not greater than the numerator. In fact, let's talk about when the denominator and the numerator have the same degree. Well, that would be same size bubbles. Okay, and the same size bubbles is only going to tell us that we do still have a horizontal asymptote, but the coefficients, the leading coefficients, the ratio of them, is going to give us our horizontal asymptotes. So y equals the leading coefficient in the numerator divided by the leading coefficient of the denominator. This will be much easier if we when we see the next example how that works. Okay, but finally, if the n is greater than the m, then we have bigger bubble on top, and this is where hopefully it'll help you. The bigger bubble on the top, this means that this bigger bubble is going to carry the fraction up and away to infinity, and therefore we have no or none horizontal asymptotes. None, because this bubble here is going to carry it, like I said, up and away. It's not going to land at any one real number that's less than infinity. So therefore, as the x values get really big, the fraction gets blown out of proportion, becomes so large that it never approaches one real number. Okay? So we're almost done. A couple more examples here, and then you guys are going to do some problems on your own. We have the horizontal, or the h of x. We have h of x defined here, and we can see that the numerator has a degree of 4, and the denominator has a degree of 3 that's a bigger bubble on the top than the smaller bubble on the bottom. This way we say we have no horizontal asymptotes. Don't forget, it's much easier to remember a story than it is to remember a bunch of math notation. So if you can picture that story of the bigger bubble on the top going up, up, and away, then no horizontal asymptote. Okay, in our last example here for finding horizontal asymptotes, again we're not finding oblique, we can see that the numerator and denominator both have the same degree. So we have same size bubble in both numerator and denominator, and so what I said was that you peel off the coefficients. The ratio of the coefficients is the horizontal asymptote, and I should write the word, or the initials ha. So our ha would be y equals 8 divided by 4. Okay, in other words, the horizontal asymptote is y equals 2. That's all you have to do when you see that the numerator and denominator both have the same degree. Now I'm going to give you some problems to do from the book, and that's going to be it. Well, here's the homework assignment. Pause the video, write these down. The rest of the video is going to, the next video will show you all the solutions, but the rest of this video is going to show you the page and problem numbers. Okay, so again, pause the video, write these down, and then I'm going to go ahead and switch over to the first page, and then you'll see in the next part of the video you'll see all the different pages. So all you have to do, if you don't have your book with you, is just to pause the video at those pages and then write down your answers. Please don't copy down any problems. Just write down the answers. There's very little work necessary. If you have to write something down, go ahead. But that's what I want to see on Monday, is all the answers to these questions. And then, like I said, the next video is going to show you all the solutions. And so all of your answers should be right. And I will expect to see those correct answers. So if you don't know if you got one right or not, then just watch the videos and correct your homework so that you can know. Well, I mean, the bottom line is make sure all of your answers are right by watching the next video. Okay? Thank you very much. So here you can see problems 1 through 12 on page 224. So do all of these problems except for number 2. I'm going to go ahead and pause the video on 3, 2, 1. I'm going to go ahead and change the slide. 3, 2, 1. Okay, here we go, 13 through 24. So you've got a few problems there. I'm going to go ahead and change the slide here. 3, 2, 1. And 26 and 30. Oh, did I not tell you to do those? Yeah, don't do 29, do 26 and 30. I messed up. I told you to do 29, but okay, so 26 and 30. And then 31 through 54. So here you go. You have all that you need now. And I'm going to go ahead, like I said, next video I'll show you all the solutions.